you can start sharing your screen.
So, let's see. Yeah, so thanks to the organizers for putting together this very interesting conference. My talk is going to be about the spatial symmetry part, not the fracton part of the topic of the conference. And so I'm going to be talking about work that I've done over the past couple of years, posted in these 2 papers that were posted starting last year with my student Naren Manjunath. And it's about classifying fractional quantum Hall states with spatial symmetries. Okay, so we all know, fractional quantum Hall states have a lot of topological invariants, Hall conductivity, fractional electric charge, fractional statistics, quantized thermal Hall conductance. And remarkably, through really incredible collaboration between theorists and experimentalists, all of these have been measured experimentally, although perhaps with varying degrees of controversy over the last 40 years, with the fractional statistics being the most recent one in the past year. So there's a kind of natural question, what other topological invariants exist and what would their physical consequences be? I think there's an opportunity that perhaps to eventually make contact with the experiment in sort of predicting new kinds of topological invariants that these systems might support. Now, when we think about this problem, I'm sure everyone is already aware, we should think about this in the sense that some of these invariants require symmetry, like Hall conductivity and electric charge require U1 symmetry, whereas the other invariants, fractional statistics, quantized thermal Hall conductance are kind of intrinsic topological invariants that are well defined in the absence of any symmetry. So the question is, given the complete symmetry group of the fractional quantum Hall problem, we'd like to know what is the full set of topological invariants, what are the physical signatures, and what kinds of microscopic situations might these be realized that we can tell our experimentalist friends potentially they could go measure. Now, for intrinsic topological invariants, we have a very comprehensive mathematical framework. This is the framework of unitary and modular tensor categories, sometimes goes by the friendlier name of algebraic theory of anyons. So this is described by some set of data which involves fusion rules, F symbols, and R symbols. And then if you add symmetry to the problem, then we also have a comprehensive mathematical theory, although it's comprehensive for the case of unitary symmetries and orientation preserving symmetries. And this is G-crossed braided tensor category, which is basically like an algebraic theory of anyons together with the symmetry defects. And the data that describes this is some data that tells you how symmetries permute anyons, and then fusion rules involving anyons and symmetry defects, and then the action of symmetry defects on anyons parameterized by additional data. And then we have G-graded fusion rules and G-crossed braiding. So there's a bunch of extra data. So what we're going to do is we're basically going to apply this theory to symmetries of interest for the fractional quantum Hall problem and kind of see what happens. So symmetry groups of interest, the most basic one is just U1 charge conservation. But if you consider systems in the clean limit, you also have continuous magnetic translations and continuous rotations. So that involves the Euclidean group, but it's really, you should think about it as a U1 central extension of the Euclidean group. And the central extension encodes the fact that translations don't commute, and we have this magnetic translation algebra. So I use this funny symbol that I learned from Xiaogang to denote the fact that we have this non-trivial central extension. Then we're also interested in the lattice case. This is relevant when lattice effects are very strong. So this would be for fractional churn insulators, for example, where you have discrete translations and M-fold rotations. And now you have some flux per plaquette that specifies the central extension. So you also kind of need to keep in mind that there's this phi as well. In general, of course, we can have multi-component fractional quantum Hall systems. So in general, the symmetry is just going to be, well, often the symmetry will be just some subgroup of this more complicated group. So the program is going to be, we're going to fix the intrinsic topological order, fix the modular tensor category, and we're going to use the G-cross braided tensor category to systematically classify all possible symmetry protected topological invariants. And then we're going to try to determine the physical meaning of these things. And the underlying assumption here is that we can treat spatial symmetries on the same footing as internal symmetries. There are a lot of general arguments in favor of this and a lot of empirical evidence. And even and more recently from studies of crystalline SPTs, there's been a lot of evidence that this does work, although it is in some sense an assumption. And then our future work is going to be to verify the predictions of this G-cross theory through numerical simulations on microscopic models, and hopefully eventually develop some specific experimental predictions. Now, this talk is going to be about bosonic systems. The theory of fermionic symmetry in topological phases is still under construction. So the first thing that we need to grapple with is the fact that G can be continuous. Okay, so this is something that has not at all been properly studied in the mathematics literature. And so we're basically completely on our own here. And the question is, how do you define G-cross braided tensor categories when G is continuous? Now, there are some choices. We can require that data that I had mentioned earlier to be continuous or piecewise continuous or measurable functions on the group. Or we could just use the discrete topology on G and forget about the fact that it's continuous altogether. Now, it turns out that these two just do not work. They give wrong predictions. And then furthermore, it turns out that these two, piecewise continuous and measurable, are actually the same for these particular symmetry groups that we study. So for these symmetry groups, at least, there's no issue, and we can just choose whichever one is depending on what calculation specifically that we want to do. That's nice. So there's three basic aspects when you include global symmetry. First is you need the group homomorphism from G into the autoequivalences of the modular tensor category that tells you how symmetries permute anyons. In this talk, I'm going to assume this is trivial. Then there's symmetry fractionalization. This is basically specified by this kind of a map for every anion, but this map is not actually gauge invariant, so it's subject to some gauge transformations. And the different symmetry fractionalization classes are related to each other by elements of the second group cohomology that showed up in Mike Hermelli's talk just now. And finally, we have the braiding and fusion of defects. So we have G-cross braiding, G-graded fusion, and these different solutions can be related to each other by elements of this third group cohomology. Now, this is a pretty non-trivial statement, right? How do I know that this is true? It turns out that when the group homomorphism is trivial, you can explicitly solve the G-cross braided tensor category equations in complete generality. That's one of the things that was done in this paper. And then in that case, you can just show that all the solutions can be related to each other by these two quantities. And therefore, so that's how you can prove this. And then the fact that what you require of the G-cross data, like whether it's piecewise continuous or measurable, just turns into what you require for the definitions of these group cohomologies. So for us, these group cohomologies can be either piecewise continuous or measurable, and it turns out it's the same for the symmetry groups that we study. And furthermore, there are redundancies that show up that you need to examine on a case-by-case basis, meaning that when you change the solution by an element of H3, for example, you don't necessarily get a new phase. You have to actually study the G-cross solutions in detail. And then, yeah, so this is what I mentioned. Piecewise continuous is the same as Borel measurable cohomology, and for our symmetry groups, at least. So when you have U1 symmetry, this is kind of already, the basic results are already well known, but we kind of can put it in this whole framework. So the idea is that the second group cohomology, this is the Borel measurable cohomology now, is given by A. So that means that we need to specify an abelian anion, that's the Laughlin quasiparticle. Then fractional charge of every anion is given by braiding with this so-called Vizon. And this is the expression for it in terms of the G-cross data. The defect class has, the H3 here is integers. So that's like adding integer quantized Hall conductivity. And then so we all know that there's a fractional quantized Hall conductivity, and we can determine what this is in the G-crossed formalism. And one of the interesting things about this is that you can determine the fractional quantized Hall conductivity from the G-crossed modular T matrix. So you can put your system on a torus with G branch cut in one direction and no branch cut in the other direction, and do a T matrix move, a Dane twist. And the diagonal, one of the diagonals of this T matrix, when you do it n times, can give you this, this Hall conductivity. Actually, maybe this n shouldn't be here, I don't remember actually. So the interesting thing about this is actually a new categorical definition of Hall conductivity. And one of the things that I'm kind of excited about with regard to this is that I think this might give a new way of extracting Hall conductivity just from a ground state wave function once we have a definition like this. Now, once you add a continuous magnetic translation symmetry, then these cohomology groups actually don't change, but what changes is now you can define a filling fraction within the G-cross theory, and within the G-cross theory, you can prove the well-known relation that Hall conductivity is the filling fraction. And I think this is interesting because we are not assuming Galilean or Lorentz invariance here. This is just directly from the G-cross data. And then we add the continuous rotational symmetry as well. Symmetry fractionalization now becomes A cross A. So this is something we already know about. We have fractional electric charge, and we also have fractional orbital angular momentum. So this is this tells us the phase obtained by an anion when it goes around some geometric curvature. So there's a contribution from this orbital angular momentum, and there's an extra contribution from the intrinsic topological spin of the particle as well. And Andrei Gromov has a nice calculation of this in this paper in like U1 level M Chern-Simons theory. The responses now, to understand the responses, we calculate this H3. This H3 is Z cubed, so there's 3 integers that specify the response in addition to the integer part of the response. So we have Hall conductivity, we have shift, and we have shift gives us the charge bound to geometric curvature, and it tells us the angular momentum bound to magnetic flux. And then we have a third quantity, which is the angular momentum of the curvature. So we have these, using the G-cross modular T matrix, we can obtain expressions for all these quantities within the G-cross theory. And all these responses are well known. There's this well-known response theory, geometric gravitational response theory that has been studied going back to Wen and Z, but then more recently it was kind of revitalized around this time period where people studied these. So this is reproducing everything that's known in the continuum case, but from this systematic G-cross framework where you're actually computing these non-trivial Borel cohomologies and the G-cross great tensor category and trying to figure out what it all means. And so you arrive at exactly what was known before. But now we can go to the discrete case and see what kind of new things that we get. So in this case, symmetry fractionalization, when you compute it for this group, it turns out that it's independent of the flux per unit cell. And you can have any rational magnetic flux per unit cell. And the group is given, has kind of 4 components here. 2 of them are kind of just versions that we already knew about before. There's the fractional electric charge given by the Vizon. Now we have something that you could call the discrete spin vector. This specifies the fractional orbital angular momentum on the lattice case. But importantly, it requires a commensuration between the order of the rotation group, which is M, and the abelian anyons. So this spin vector is going to be non-trivial only if there's some commensuration between the anion fusion and the point group symmetry. But in addition, there's 2 new quantities. There's fractional linear momentum, which is described by 2 anions, but there's an equivalence relation among them. That gives us a discrete torsion vector. This is only non-trivial with 2, 3, and 4-fold rotational symmetry. And then there's a fractionalization of the translation algebra, which is colloquially sometimes called the anion per unit cell. So this has been discussed quite a bit in the past. Sometimes this last one is what was referred to as crystal momentum fractionalization, but it's really fractionalization of the translation algebra. So there's really something new here, which I don't think was pointed out ever before, as far as I'm aware, that there's this extra piece in the symmetry fractionalization, which is only non-trivial with these point group symmetries. Now, when you look at the responses, you calculate H3 to get the integer part of the response that's given by this group. This Km is something that I had written over here for 1-fold, 2-fold, 3-fold, 4-fold, sorry. 2-fold, 4-fold, 3-fold, and 6-fold symmetry. So now we have 9 fractionally quantized responses. In addition to the Hall conductivity, we have the discrete version of the shift, which binds fractional charge to lattice disclinations and angular momentum bound to magnetic flux. So this defines what you could call a fractional higher order topological insulator. We have angular momentum of a disclination. Then we have something really new. We have fractional quantized charge polarization. This binds fractional charge to lattice dislocations, and it binds linear momentum to magnetic flux. And we have a fractional quantized angular momentum polarization, which binds angular momentum to dislocations. We have filling fraction, charge per unit cell, angular momentum filling fraction, linear momentum filling fraction. And then we have what's a fractional quantized torsional response, which is a linear momentum of the dislocation. So 4 through 9 only occur in the discrete case on the lattice. And furthermore, 4 is only non-trivial when you have 2, 3, and 4-fold rotational symmetry. 9, you can write down a geometric torsional response in the continuum, but it's not quantized. So here we find that it is quantized. We have fractional quantized value for this guy, which is non-trivial in this lattice case. So I'm out of time, so I can't actually explain anything more about this stuff. So I had a few slides in case I did have time, so I'm just going to skip them. Yeah, so then you can use this theory to just explicitly count like how many different fractional quantum Hall states you would have on, say, a square lattice when you fix your topological order. So like there are 576 distinct phases on the square lattice with just 1/2 Laughlin topological order, assuming you fix the integer part of the Hall connectivity, filling fraction, angular momentum. So using all these invariants that we found, you can completely pin down which of these phases you have. So I'll just end with the summary of the fractional quantum numbers and fractional quantized responses in this table just up here. Thank you.
Okay, thank you. So questions? Dominic?
Hi, yeah, I have a question for Maissam. So